In this module, we will discuss different robust regression techniques that are employed by statisticians when there are outliers present in the dataset. When we decide on fitting a particular model to a dataset, we want the datasets to fit the model perfectly or at least near perfectly. But sometimes there are one or two data points which are extreme values, which are extremely high or extremely low related to as in relation to the other values of the data. So, in order to remove these outliers or extreme value, we have to use different methods. In this module, we will discuss the different robust regression techniques which will help us in ignoring the effect of these outliers in the model and get the estimates of the regression parameters and draw inferences about them.
Introduction to detection of outliers. When we are fitting a regression model, while most of the observations fit the model and meet the Gauss Markov conditions of linear models, at least approximately, some of the observations do not. This situation might occur if there is something wrong with one or more of the observation or if the fitted model is not appropriate. Since there are two reasons for the existence of observations that do not belong to the model, we have two purposes of trying to identify them. The first is to protect the model from any observation that do not belong to the model and thus adversely affects it. And second, to find the shortcomings of the model that we have fitted. Observations that do not belong to the model exhibit numerically large residuals, and when they do so, they are called outliers. In order to detect the outliers, one may go back to the original dataset and use subject specific knowledge to study the outliers and explain the origin, or one should investigate whether the fitted model is a failure. For instance, if the relationship between the explanatory variable and the response variable is quadratic, then just fitting a linear regression model will not suffice. Let us look at the definition of outliers. Any unusual observation in the context of our study will be called outliers. There are three types of outliers in a regression setup: the outliers in responses or the y variables, outliers in the explanatory variables or the x variables, and outliers in both y and x variables. Now, an observation which has an inordinate influence on the regression curve is called an influential point. Outliers frequently have an inordinate influence on the least squares estimate in a regression setup, although not all influential points have large residuals. Outliers may or may not be influential. Whether an outlier is influential or not is a matter that we would like to test. Residuals are used to detect outliers in responses y, and leverages are used to detect outliers in the independent variables x. Now let us look at the graphical representation of outlier effect. Suppose we have 10 pairs of data points xi, yi, where yi is our explanatory variable and xi is the response. The least square solution fits the data very well, and we can see from the following plot that when we plot the points and the regression line, they perfectly coincide with each other. However, suppose that someone gets a wrong value of yi, or if one value of yi is different from what we had in the original dataset, and that point happens to be further away from the remaining values of the yi variable, then the pair yi-xi will be rather far away from the regression line. The following plot reveals that the point is going to be an outlier in the y direction, and the regression line that we have plotted using this dataset is now tilted. The outliers, which are the influential points in the response variables y, have received most attention in statistical literatures because we usually consider the response variable, which is yi, as observations and xi as fixed numbers. However, usually in real life, the explanatory variables are also observed quantities and are subject to random variability. Therefore, there is definitely reason to believe that gross error can also occur in explanatory variable xi's. Now, referring to the regression line plot in a couple of slides earlier, we had seen that the least square fit the data perfectly. Now, suppose in the same data set, one of the values of x is different. And it is so different that when we fit a regression line using the least squares technique and we plot the regression line, we see that under the influence of the changed x value, the regression line completely tilts in the opposite direction. The resulting point is called an outlier in x direction, and its effect on the least square estimator of the parameters regression appears to be very large because it actually tilts the least squares line in the opposite direction. The outlier point in x direction is called the leverage point. Now, regression outliers, either in the explanatory variable x or in case of response variable y, pose a serious threat to the least squares analysis of a regression model. In order to handle such problem, there are basically two ways out. The first is by constructing regression diagnostics. In this method, we can fit a regression model to the data and find the diagnostics and detect outliers, and then remove them from the data set and then fit a regression model to the fresh data set. Or we can use the robust regression techniques where we do not remove the outliers from the data set, but we use, instead of the least squares method, other robust regression techniques under which the parameter estimates are not influenced by the presence of outliers. Now let us look at the uses of regression diagnostics. Diagnostics are certain quantities which are computed from the data that we have at hand in order to single out the influential points, after which the outliers can be corrected or removed, followed by the least square analysis of the remaining cases. In case of one or two outliers, it works well by just deleting the influential points and by fitting the regression model again. However, if there are multiple outliers present in a dataset, then this method is not going to work. In robust regression techniques, we try to devise estimators that are not so strongly affected by outliers. Although some statisticians believe that in the robust methods, the purpose is to simply ignore the outliers, it is not so in reality. In this method, we look at the residuals and parameter estimates from a robust regression analysis. We use robust techniques so as to eliminate the effects of unusually high residuals which happen due to the presence of outliers. But when comparing the two methods, the diagnostics and the robust regression techniques basically have the same goals, but just in the opposite order. Using diagnostic tools, we first try to delete the outliers and then fit the data by the method of least square. However, in the robust analysis, we first fit a regression to the data and then identify those points as outliers that possess very large residuals from the robust solutions. Now, in connection to outliers and leverages, one very important matrix that we come across is the hat matrix. Suppose the regression equation is given in the matrix form by y equals x beta plus epsilon. Then the hat matrix is defined as H equals x times x prime x inverse x prime. The elements hi of H may be interpreted as the amount of leverage extended by the ith observation yi on the ith fitted value. The leverages HII are the diagonal elements of the hat matrix. Consequently, an individual leverage is given by Hij, which equals xi prime times x prime x inverse xj, and the diagonal elements Hii is given by xi prime x inverse xi. Here Hii are the standardized measure of the distance of the ith observation from the center or centroid of the X space. Now the hat matrix, besides being very important in terms of leverages, also has some very interesting properties. Let us discuss them in detail and I will derive each of these properties. The first property is that the ordinary least square residuals in case of a regression setup is given by I minus H times Y, where Y is the vector of response, I is the identity matrix, and H is the hat matrix that we have just discussed. The residuals Ri equals the difference between the actual response Y and the estimated response Y hat. So we can write Ri equals Y minus Y hat. Y hat can again be written as x times beta hat, where beta hat is the vector of estimated regression coefficients. Ri equals y minus x times beta hat, where beta hat is the vector of estimated regression coefficient that takes the form x prime x inverse x prime y. Replacing beta hat by this expression, we now have Ri equals y minus x times x prime x inverse x prime y. And from the definition of the hat matrix, x times x prime x inverse x prime is H. Hence, writing H in place of this expression, we now have Ri equals y minus Hy, which equals I minus H times y. The second property of the hat matrix is that the matrix I minus H is symmetric. In other words, I minus H prime equals I minus H. So if we transform the rows into columns in this matrix I minus H, we get the same matrix. The third property of the hat matrix is that I minus H is idempotent. That is, when multiplied by itself, I minus H gives us the same result, I minus H. First, let us look at the hat matrix H. If we multiply the hat matrix H with itself, we have H prime H. Now replacing matrix H by its expression, we have x times x prime x inverse x prime x prime x inverse x prime. Since we know in the center we have x prime x multiplied by x prime x inverse, the resultant is the identity matrix I. Hence, H prime H reduces to x times x prime x inverse x prime, which is by definition the hat matrix H. Now, to show that I minus H is also idempotent, when we multiply I minus H with itself, we get the resultant matrix in the form I minus 2H plus H times H. However, because the hat matrix is itself idempotent, then H prime H equals H. So, the above resultant reduces to I minus 2H plus H, which equals I minus H. And finally, the last property of the hat matrix, variance of the residuals is given by sigma square times I minus h. We can show that this property holds through a number of steps. Let me start with variance of residual I, Ri, equals variance of I minus h times y. Since we have proved that the ordinary least square estimates of the residual is given by I minus h times y. Therefore, variance of Ri equals I minus h times variance of y times I minus h prime. We know that yi equals xi beta plus epsilon I, where epsilon I follows normal distribution with mean 0 and variance sigma square, and that ei and xi are uncorrelated. Hence, after a few steps of simple algebra, we arrive at the final result, variance of yi equals variance of ei equals sigma square. As a result of the preceding reasons, variance of residuals Ri equals sigma square times I minus h times I minus h prime. Since we know that I minus h is symmetric, hence I minus h prime can be written as I minus h, and I minus h being idempotent, we can write I minus h prime as I minus h. And we also know that I minus h is idempotent, so I minus h times I minus h equals I minus h. The result is variance of residual Ri equals sigma square times I minus h. Now let us discuss a few robust regression methods that will help us estimate the regression parameters without the influence of outliers acting on it. In regression analysis, we obtain the estimates of the parameters using least squares method. The basic idea in this method is to make the residuals as small as possible. The reasons for the popularity of this method is its simplicity and the easy computation involved in obtaining the parameter estimates. But analysts began to realize that data sometimes have outliers, and when there are outliers in the dataset, they tend to influence the regression model, and they often dramatically affect the quality of the analysis, and the amount of effect the outliers have on the estimates of the parameters is quite large. Now, in the case of least squares estimates, we minimize the sum of square of the residuals. However, in case of presence of outliers, some of the residuals are very high, and that inflates the square of the residual, and in turn it increases the sum of the square of residuals. So in place of square of residuals, we might use something else and perform the estimation of the regression parameters. The first method that we will discuss here is the least absolute value estimator. A number of robust regression techniques have been used to detect outliers and to eliminate their effects in the estimation of the regression parameters. A first step in this direction came from Edgeworth. He reasoned that outliers have a large effect on the least squares because the residuals Ri's were squared and we were then taking the sum of the squares. So instead, he proposed the use of the absolute value of the residuals, take the sum of the absolute values, and then minimize this function to obtain the estimates of the regression coefficients. Another method that we can use for robust regression technique is the M-estimator technique. The next step in this direction was the use of M-estimator. The basic idea of replacing the squared residuals by another function of the residuals yielded the M-estimators, where in place of the absolute value of the residuals as we did in least absolute value estimators, we now use a function rho of the residuals. we take the sum of this function and minimize the summation of the function of Ri's to obtain the estimates of the regression coefficient, where the function rho here is symmetric with a unique minimum at 0. The second robust regression technique that we can use to obtain the estimates of regression coefficient is the least median square estimator. In the previous two robust methods, namely the least absolute value method and the M-estimator method, we have seen that the square function of least square technique was replaced by other functions. We can also think of a robust method where the sum is now replaced by the median, which is very robust. This gives us the least median of squares estimator, in which case we find the residuals, we take the squares of the residual, and we find the median of the squared residuals and minimize this function to obtain the estimates of the parameters. The least median square estimator is clearly equivariant with respect to linear transformations on the explanatory variables because the function only makes use of the residuals. The next method of robust regression we can use is the least trimmed square estimator. Although the least median square estimator that we have seen in the previous slide is very robust, but unfortunately the LMS performs poorly from the point of view of asymptotic efficiency. To repair this shortcoming, Rousseau introduced the least trimmed squares estimator, which was given by minimizing the sum of the square of residuals by taking the sum over I equals 1 to h, where h is less than n. N is the number of observations in our data set. So what we basically do here is we obtain the residuals, we square the residuals, and then we order them in increasing order and use the first h square of residuals to find the sum and minimize this function to obtain the estimates of the regression coefficients. The least trimmed square estimator is very similar to the least square estimator. However, the only difference is that the largest square residuals are not used in the summation. Thereby, it allows the fit to stay away from the high outliers. The last method of robust regression that we will discuss here is the weighted least square estimator. In order to improve on the crude LMS and LTS solutions, and in order to obtain the standard quantities like the t-values, confidence intervals and such, we can apply the weighted least square analysis based on the identification of the outliers. For example, we could use the following weights before we perform the least square estimation procedure. We can use the weights as follows. Wi equals 1 if residual divided by sigma hat is less than 2.5, and Wi, which is the weight, equals 0 if absolute value of residual I divided by sigma hat is greater than 2.5. This simply means that the ith observation will be retained in the weighted least square if its LMS residual is small to moderate, but disregarded if it is an outlier. The bound that is used, 2.5, is of course not completely arbitrary. It is quite reasonable because in the Gaussian situation, there will be very few residuals larger than 2.5. Instead of discrete rejection points, we can also think of continuous functions for range. For instance, we can use absolute value of Ri divided by sigma hat lying between 2 and 3 to give the weight 1, and then weight equals 0 otherwise. We have discussed here 5 different robust regression techniques that we can use to obtain the estimates of the regression parameters. There are several different regression diagnostic techniques To single out influential points in regression settings, we will dedicate a separate module for their discussion.
So, in this module, we have seen in detail how we can use different robust regression techniques to fit into a data set when there are outliers present. When we have reasons to believe that some of the data points are outliers, then using any one of these robust regression technique reduces the amount of effect that the outliers have on the resulting estimates of the parameters and their related inferences.